Okay, 4.2 is on factoring quadratic equations, and so I think this is a better way to do um, to find the solutions of a quadratic equation or to find the roots of a quadratic function than graphing. Okay, so factoring you learned about in Foundations and Pre-Calculus 10. So this is going to be kind of a review of that. Okay, so we know that football, soccer, and basketball and volleyball are just a few examples of sports that involve throwing, kicking, or striking a ball. Each time a ball or projectile sails through the air, it follows a trajectory. So that's a trajectory. It's a parabolic path that can be modeled with a quadratic function. Each of these sports is also played on a rectangular playing area, and the playing area for each sport can be modeled by a quadratic equation as well. And so when we looked at an example in the last chapter about the corral, and it had a length and a width that both had an x in it, so you ended up with an x squared term, that's an example of that. Okay, so for women's indoor competition, the length of the volleyball court is twice the width. Okay, x represents the width, and 2x represents the length. Okay, so that would be, sorry, width times length. I wrote it in the wrong order. You can say the area is 162. That equals x times 2x, so 2x squared equals 162. And so if you wanted to write it in as a standard form quadratic equation, it would be 2x squared minus 162. Okay, so if you graph that quadratic function, and how many x-intercepts are there? I can just do this one quickly on the graphing calculator. Okay, so I just typed it in there, and I can see that I have a graph, and it opens up. It's my parabola. I know it opens up because my a value is positive. Okay, and it looks as though it crosses the x-axis at values of 9 and negative 9. Okay, so we can just continue on with these questions. How many x-intercepts are there? There are 2, and what are they? 9 and negative 9. Okay, from your graph, what are the roots of the quadratic equation? Okay, well, we know that 9 and negative 9 are the roots of the quadratic equation, and we know that because I guess in our last section we learned that the roots of the quadratic equation are the same as the intercepts or the zeros of the quadratic function. Okay, so in this context, are all the roots acceptable? Well, does it make sense to have a width of negative 9? And so the answer would be no. Okay, no negative widths. All right, so even though the math tells us we have 2 possible solutions here, we don't, because according to the example, it doesn't really make sense to have a negative answer. Okay, so factor the left side of the quadratic equation. If you take a look at this, 0 equals 2x squared minus 162, and I hope you remember that the first step when you're factoring is always to take out any common factor. Okay, so since they both have a factor of 2, we can take out a factor of 2. Actually, I should have just divided both sides by 2, okay, because since that's a 0, we don't, a constant like 2 will not give us a root, right? If that's an x, you can't divide both sides by x, and the reason for that is because x could be 0, but you can divide both sides by 2. And so that 2 actually just goes away. Okay, it's not going to affect what our roots are. And then maybe you recognize that as a difference of squares. And when you have a difference of squares, remember it would be x minus 9 times x plus 9. Okay, and so if you graph this again now in factored form, you can take a look and see if I put x minus 9 times x plus 9. Okay, and actually, since it just asked us to factor it, it didn't really ask us to find the solution. I really should have left that 2 in there. Yeah, I will. I'll leave that 2 in there. Okay, so if I were actually solving it, I could take the 2 out, but since it's just asking me to factor the left side, I need to leave the 2 in. Yeah. Okay, and I'll show you in a second what happens to the graph if you keep the 2 out. Okay, so I'm just going to type that in. Okay, that was 2 times x minus 9 times x plus 9. Okay, and then when you graph that, graph them both. It'll graph the red one first and then the green one right on top, and that just shows you that they're exactly the same function. Okay, so we can factor it. It doesn't change the function in any way. Okay, how is the graph factored form related to the x-intercepts of the graph? Well, if you see, if you look at those factors, you have x minus 9. Okay, this is equal to 0 if x equals 9, and this equals 0, or x plus 9 equals 0 when x equals negative 9. Okay, so that's how it's related to the x-intercepts of the graph. So how can you use the x-intercepts of the graph to write a quadratic equation in standard form? Well, what you can do, and this is not going to tell us completely what we need to know, but if you take x minus r, okay, because when x equals 9, that would give us a factor of x minus 9. So when x equals r, that gives us a factor of x minus r, okay, times x minus s. And that can give us our quadratic equation. Okay. And the thing that's missing here is possibly another factor. Okay, that factor would actually equal a if you multiplied it out. Okay, so you do need to have an unknown factor there. Okay, so just by knowing the x-intercepts, you don't necessarily know the shape of the graph, but you will have the zeros. And I'll just show you, if I had taken that 2 out and left it out, so if I had just written this as 2, or sorry, no 2, x minus 9 times x plus 9. Okay. And now if I were to graph that, okay, you're going to get a graph with the same intercepts. Okay, but this is actually a little bit wider graph, okay, which you expect because you're going to have a smaller a value. Okay, and so if I zoom out, you can see definitely there's a difference in shape, right? There's a difference in the location of the vertex. Okay, and so yeah, you do need to know that that constant that it's multiplied by. Okay. Okay, so let's just continue with the lesson here. Next page. For men's sitting volleyball, a Paralympic sport, the length of the court is 4 more than the width. The area of the court is 60. Okay, so if x represents the width, write a quadratic equation in standard form to represent the area. Okay, so we got the width equaling x. Okay, we know the length is 4 more than that. Okay, and we know that the area is 60. Okay, so if we say area equals length times width, then we know that 60 equals x plus 4 times x. Okay, so we do a distribution here, x squared plus 4x. Okay, and then if you put that, subtract 60 from both sides, just so you have that all of everything on one side and then a 0 on one side. That's the standard form quadratic equation. Okay, graph the corresponding quadratic function. So f of x equals x squared plus 4x minus 60. Okay. Okay, what do we get? I'm going to zoom in on that. I think I see intercepts at about 6 and negative 10. Okay. All right, so how many x-intercepts are there? 2 intercepts. They are 6 and negative 10. Okay, use the x-intercepts to write your graph, or your graph in step 3 to write the quadratic equation x minus x minus r, so that'd be x minus 6 times x plus 10, okay, because obviously the sign is going to be opposite, equals 0. Okay, that's the quadratic equation in that form. And graph the corresponding quadratic function and compare it. So x minus 6 times x plus 10. All right. Okay, and I put those in and we'll just graph it and see. And you can see them. They come on top of each. It's like the green one comes right on top of the red one. So, so we know that it's the same graph. Okay, so in factored form, it is the same graph. Okay, well, that's what it asks us to just compare them. Okay, so how does the factored form of a quadratic equation relate to the x-intercepts of the graph, the zeros of the quadratic function, and the roots of the equation? Okay, well, I guess when you have a factored form, and say it's in the form like this, x minus r times x minus s. Okay, then you know that r and s are the x-intercepts of the graph. They are the zeros of the quadratic function, and they are the roots of the equation. Okay, so we could use a quadratic equation like 0 equals x squared minus 5x minus 6. And if we wanted to find the roots, instead of having to graph that, okay, which isn't always a possibility, we can factor that. Okay, so if you remember how to factor this, notice there's a 1 in front of the x squared, so it's a pretty easy one to factor. Okay, what we want to do is you want to find two numbers that are going to multiply to give us -6 and add to give us -5. Okay, and so we're going to say, you can do this in your head, you can do it on paper, I'll just show you. -6 can be a result of multiplying -6 and 1, or 6 and -1. Okay, and I mean, I happened to list the first one, the one that works first, okay, because I would just check them every time. -6 plus 1, those two numbers do add together to give us -5. So I'm basically done here. If I'd had to, I could have continued through all the factors. Okay, and it's good to do it either going down from 6, so you go 6, 5 doesn't work, 4 doesn't work, 3 works, so it'd be -3 and 2, or 3 and -2. And then I know that because those two numbers are right next to each other, then I know that I've done all the factors that are possible. Okay, so I can rewrite this as, okay, x minus 6, x plus 1. Okay, so in order to find the roots of that equation, I would say that the root would be x equals 6, and another root is x equals -1. Okay, so if the roots of a quadratic, okay, so just notice these signs are switched because when x equals 6, okay, then x minus 6 equals 0, right? Because if x is 6, that becomes 6 minus 6 equals 0, right? Okay, and so if the roots of a quadratic equation for number 7, if the roots are 3 and -5, then a possible equation would be x minus 3 times x plus 5 equals 0, okay, which if you expanded it would be x squared plus 2x minus 15 equals 0, okay? So that would be a possible equation. And remember, why is that just a possible equation and not necessarily an equation, or the equation? Because you might have had a constant value here, okay? Just some number that you multiplied everything by. And we looked at that example where you would have the same roots, but a different shape of graph. All right, I think that's just about it for this one. So yeah, just a little review here of how to factor. I think that I'll do this in the next video. So I'm going to stop this one here because it's getting long, and then this is where I will pick up in the next one.